Hey, what's up guys, this is Guy here with KBTrainings. Today we have the lesson number 3.2.4. We are still seeing OSPF version 2 and today we are going to talk about neighbor adjacencies. This is for our course on the Cisco CCNA 200-301, and if you're watching this on YouTube, the course is available on kbtrainings.com/CCNA. That's where I bring you from zero to engineer by preparing you for the Cisco CCNA 200-301 exam that can help you start or boost your career in this field. Neighbor adjacencies is one of the topics, and if we pull up the exam blueprint, you can see that under OSPF version 2, Cisco is asking us to learn about neighbor adjacency and what is happening when two routers are trying to be OSPF neighbors. And this is what we're going to cover today. I'm going to talk about neighbor adjacencies in general, what it is and why we have to learn it, and I'm going to give you the conditions that need to be met for two routers to become neighbors. And also we're going to see all the different states that you can find in OSPF neighbor adjacencies, and also we're going to finish by doing a lab in Packet Tracer. Of course, I've always said that Packet Tracer, or the lab in general, is where you should spend most of your time. We're going to see the theory, but we're going to practice. That's where you're going to master or understand fully what we are going to cover today. So we're going to finish with a lab inside Packet Tracer. So to start, when you have an OSPF topology or when you have two OSPF enabled routers, those routers cannot do anything if they are not neighbors. So they need to start by establishing that neighbor adjacency so that they can communicate and exchange their link state database. Let's say we have a router 1 here and a router 2. So before we move forward, I need to mention that in this course, or specifically for the CCNA, we are just covering two types of network. As I told you last time in the last lesson, we are only seeing broadcast and point-to-point. So we're focusing on broadcast networks and point-to-point networks. And in these two types of networks, when you are connecting two OSPF enabled routers, they need to discover each other to become neighbors. So the neighbor is discovered dynamically in these two types of networks. If you have like the NBMA or non-broadcast multi-access network, if you are in this kind of network, you may have to configure the router manually. You need to go into configuration and let your router know which other router should be neighbored to it. But in our case, we are discovering the neighbors dynamically using the hello packet. So when you connect these two routers, they're going to send hello packets to each other, and they're going to discover each other and then grow their neighbor adjacency to become fully adjacent. When we say fully adjacent, it means that they have the same copy of the link state database. So that is what fully adjacent means. So we're going to see exactly the different steps that are involved in this neighbor adjacency process and what are the conditions that we have to consider in this relationship. And I also mentioned fully adjacent. What does that mean exactly? We are going to see in the next slide that we have different states of neighbor. So when you have routers in the OSPF topology, in the point-to-point, for example, we only have two routers involved, 1 and 2. These two routers have to be neighbor, have to be fully adjacent. They have to have the same copy of the link state database to be able to run the algorithm and generate the routing table from the OSPF data that they have. But if you are in a broadcast network, there is a new notion that is introduced here. I've talked about it, but we're going to go in detail in the next lesson. We have a notion of DR, or designated router, and BDR, or backup designated router. So only these two routers are allowed to form a full adjacency with all the other routers inside the topology. So only these two routers will have the copy of, will have the same copy of the link state database with all the other routers inside the topology. So in the next lesson, I'm going to tell you more about these two roles. So that's why when you are in a broadcast network and you have, let's say, 4 routers, 1, 2, 3, and 4 connected to the same Ethernet network segment, for example, and 2 is the DR and 1 is the BDR. These two routers, 3 and 4, are going to be fully adjacent only to 2 and 3. but between them, they're going to stop at a certain state, which is called two-way. So they're going to know each other, they're going to know they exist, but they will not share the copy of the databases. Everything will come from the DR or the BDR. That's going to be for the next lesson, but it's really important to understand the next step that we're going to see here, or the different state that I'm going to show you. So let's go and talk about the conditions that you need before you can become neighbors. So when you are in OSPF topology, two routers can become neighbors, or two interfaces on which we activated OSPF can form this neighbor adjacency only if these conditions are met. First of all, they need to be in the same area. Both your interfaces need to be in the same area, in the same OSPF area. So this interface should be in the area 0, for example, and this other one should be in area 0. If you have 0 here and 1 there, it's not going to work. And by the way, I need to mention that the process ID doesn't matter in this case, because we know that we always do IP, OSPF, and then the process number. So the process number is not relevant in this case. It might be different from router to router. The second condition is that you need to have the same authentication configuration. If you are using a password or MD5 password or any kind of security on one end of the link, you need to have that same authentication configuration on the other end to be able to become neighbor. Otherwise, you won't be able to do that. They need to be in the same subnet. So if you have a /24 in this interface, the other end should be in /24 as well. The next condition is to have the same hello and dead intervals. We know that by default for a broadcast network, the hello interval is 10 seconds and the dead interval is 40 seconds, or 4 times the hello interval. So if you have 15 seconds here and you have 10 seconds on the other end, you're going to have a mismatch, and these routers will never become neighbors on this link. I'm going to show it to you in packet trail, so we're going to do these manipulations and see exactly the messages that we have and how we can prevent two routers to become neighbors. All right, these are the conditions. There is another condition that I didn't want to mention here because it talks about stub areas and stuff. So that's not covered in this course, so I'm not going to mention that. But for now, these are the 4 main conditions that we have to meet before two routers can become neighbors in OSPF. So now we're going to talk about the different neighbor states. These are the different states that you can find between two routers. And when you have two routers and they're trying to become neighbors, they go through these different states here that I'm going to tell you. The first one is down. The second is attempt. We need to know that for the attempt state, this is just for NBMA, or non-broadcast multiple access, and we know that we don't cover that in this course, of course. So this is not going to be one of the states that we're going to find in a broadcast or point-to-point networks. And then we have the init state, the two-way, the X start, the exchange, the loading, and the full. So I'm going to give you some details on these different states in the next slides. So next, we're going to start with the down state. This is the very first state of neighbor in OSPF. So when you have the router 1 here and the router 2 there, they don't know each other, there's nothing happening, they are down. This is the state where they start and they move on to become neighbors. That's the first state. And also, if we already have a neighbor adjacency between these two routers, and for some reasons, let's say this interface goes down. When the interface on the router 2 goes down, router 2 knows about it because the interface is on router 2. So directly router 2 will put the neighbor state for router 1 to down, and router 1 will not be a neighbor anymore. You will not find it in the neighbor table inside the router 2. But when we go to router 1 doesn't know about the state of this interface on router 2. It only relies on the hello packets that are coming from router 2. So we know that the hello timer or the hello interval is 10 seconds, the dead is 40 seconds. So if the dead interval is set to the default value of 40 seconds on this router, and 40 seconds goes by without any hello packet coming from the router 2, the router 1 is going to consider router 2 dead, and it's going to forget about it. That's actually the term. It's going to forget router 2, and the state of this for the neighbor 2 will go down. So it will be down and flushed from the neighbor table in router 1. That is the down state. The following state is the attempt state. As I said, this is for NBMA networks, and we're not going to cover NBMA because in these networks you can configure, or you configure the neighbor manually. You need to manually tap the command to show your router, to instruct your router to become a neighbor with another router. And if you do that, and for some reasons the router or your router doesn't receive any packet or any information from the neighbor, it's going to put it in attempt mode. It will keep sending hello packet at a certain rate, hoping to receive a response from the neighbor. Because you configure the neighbor manually, there's no way for the router itself to flush the neighbor out of the table. You need to delete that command, but meanwhile it's going to keep sending those hello packets to get the response from the neighbor. So this is the attempt state. The next one is the init state. In this state, a router has received a hello packet from the neighbor, but it didn't see its router ID inside that hello packet. As we know, when we talked about the different packet types in OSPF, we know that one of the fields in the hello packet is the neighbor. So there is a list of neighbors that can be found inside the hello packet. You have, of course, the router ID, the subnet, the data interval, and so on. You also have the neighbors. And if the router doesn't see itself inside the hello packet that it receives from another router, it's going to, of course, have that router in the neighbor table, but the state of that neighbor is going to be init because we don't see each other. We don't have bidirectional communication between each other. That is the init state. And then after that, the routers can go to the next state, which is the two-way state. The two-way state is when the routers have seen each other. So the routers can find their router ID inside each other's hello packet. The router 1, for example, and the router 2. The router 1 has the router ID of 1111. Router 2 is 2222, and they are connected. They send each other hello packets. So when router 2 receives a hello packet from router 1, it can see inside of it that router 1 knows about it. So under the neighbors, it's going to find its router ID. That's the two-way. And in the router 1, when it receives a hello packet from the router 2, it's going to see its router ID inside the hello packet. Here we are at a two-way state. At this state, the routers can decide to move on with the neighbor adjacency and become fully adjacent, or they can stay in this state depending on the configuration. So I told you about the DR and the BDR, designated router and backup designated router. These are the two types, the two roles of routers that we're going to see in the next lesson. So in the broadcast topology, not all the routers can become fully adjacent. All the routers are only fully adjacent with the DR and the BDR. So that's what we're going to cover. And if you are not a DR or a BDR, let me show you here. Let's say we have a small broadcast network here with 4 routers that are sharing this same Ethernet segment. So let's say router 1 becomes the DR and router 2 becomes the BDR. The router 3 and the router 4 are going to be fully adjacent only with router 2 and router 1. Between them, they are going to stop at the two-way state, which means they know each other. They see each other in their hello packets, but they are not fully adjacent, which means that they don't share their copies of the link state database. However, they share the same copy with the BDR and the DR. So it's up to the DR to synchronize its version of the link state database with the router 4 and the router 3. That's how it is. This is just to avoid a lot of noise inside our network when it comes to OSPF. We're going to cover this in detail in the next lesson. That's all I can say for now. So the two-way state is where, by the end of the two-way state, we will have the DR and the BDR election already, and the router will decide if they have to become fully adjacent or stay in this state. So if they decide to become fully adjacent, they go to the next state, which is the XStart state. This is where they negotiate the number or the initial sequence number that they're going to use to exchange the information. Here we're going to have an election of a master and a slave. So in this order, the master will be the one polling for information from the slave. So the master will be requesting information from the slave so they can start the exchange of what they have in their link state database. And after that, they go to the next step, which is the exchange step. In this step, the routers are going to exchange the DBD or database descriptors. These are the kind of packets that are going to give them details on what they have inside their tables and see what information they need to actually exchange or get from each other. And after this step here, we have the loading step. This is where the routers actually exchange the information. They send each other the link state information that they have inside the databases. And we also have to know that if there is any information that is incomplete or look outdated, the information is going to be put in the request list. And the request list is where the LSR are coming from. So the link state requests are coming from the information that we have in the request list. And we send this to the neighbor to get some information. And when we are sending an update to the neighbor inside a link state update, we are putting this information in what is called the retransmission list. The retransmission list is a list of updates that we have sent and we have not received acknowledgement for those updates. And as soon as we receive a link state acknowledgement from the neighbor, we're going to remove that information from the retransmission list, and we'll keep going with all the database sharing. So when the loading part is done, then the routers become fully neighbors. So they go in the full state. In this state, the adjacency is complete. They have the exact same copy of the database, and they are now able to run the OSPF or the Dijkstra algorithm to find exactly what is the shortest path to all the destinations that are known inside the network. So these are the different states that you find when it comes to neighbor states. And then next, as I said, we're going to spend most of our time in packet tracer. So I'm going to do a quick lab here. Actually, not very quick. We're going to spend some time in this lab. And these are the commands that we're going to use. Actually, I'm going to show you something new today. We haven't done it in this course at least. It's the debug command. The debug command is really useful when you're trying to see what's happening in the background. When you're trying to see exactly what kind of events you have in your router, you can run this command. For example, right now we're trying to see what kind of OSPF events we have. We will do debug IP OSPF event, and you're going to see the result when we will do it. And when you activate the debug on your router, you need to deactivate it when you're done with it, and you run the command undebug all, or you can just say u all. This will stop all the debugging that was happening in your router. I'm going to show that really soon. And these are the commands where you can see the neighbors. You do show IP OSPF neighbor. This will show you the list of neighbors that you have in your database. And you can also change the hello interval or the dead interval in your router. I'm going to do this just to show you the messages that we have when there is a mismatch, and we will exactly see what's going on. So as I always said, spend your time practicing, because that's where you learn the most, and that's what I'm going to do with you here. So let's go in packet tracer and we're going to do some practice. So I have packet tracer here, and now I'm going to create a quick topology with 3 routers. I'm going to grab this 1, 2, 3, and then we have a switch in the middle. I'm going to create a broadcast network with 3 routers. One of them will be misconfigured, so we see exactly what kind of messages we have. And also I'm going to put some sniffers, actually 2 sniffers between each router and the switch, so that we have traffic coming from each side, and we can analyze the traffic and see exactly what we have inside those packets. So I have a total of 6 sniffers here, and this is a network. Subnet is 10.0.0.0/24, and this router will be, actually let me give them some real names and host names. So this is the router 1. I'm going to name it router 1, and the host name will be router 1. This is the router 2. Host name will be router 2. And this is the router 3 with the host name of router 3. Oh, it says 3. I don't like router 0. I always change it to router 3. All right, and for the IP addresses, here will be .1, .2, and .3. Okay, so now let me connect these different devices from the router to the sniffer, sniffer to sniffer, and sniffer to switch. All right, so Now I just have to configure the sniffers. Let's go in the first one. Make sure that we are configuring the interfaces the right way. Like in this case, we are listening to Ethernet 0, so the port 0. We clear everything and we only select OSPF because we are only doing OSPF right now. So the next sniffer, we're going to listen to the port Ethernet 1 because this is the port facing the switch, and we are going to clear everything and only enable OSPF. Alright, so in this router, in this sniffer, we're going to listen to the Ethernet 1 and clear everything and only select OSPF. Alright, in this one, we're going to listen to the port 0. Did I say 1 on the other one? Yes. So in this one, we listen to 0, we clear everything, and we only select OSPF. Same thing for these ones. So here we're listening to 1, clear everything, and only select OSPF. Alright, in this we are listening to 0, 0, we clear everything, and we only select OSPF. Alright, so now we have to configure the routers. I'm going into router 1, and I'm going to configure the interface number 0/0 with the IP address of 10.0.0.1/24, and I'll do a no shot to enable that interface. I'm also going to change the IP OSPF hello time to 15. I will change that time as well to 60, which is 4 times 16, and I'll do IP OSPF 1 area 0 to activate OSPF on this interface. As soon as we do that, if we come to this sniffer here, we can see that we have hello packets being sent every 15 seconds because that's what we configured. And if we open the hello packet, you can see that we have the router ID, which is 10.0.0.1. I didn't configure this, but this is the automatic configuration, which is the highest IP address on the physical interface. And we have the area ID, which is a 0. We don't have any authentication here. And this is the subnet mask for our topology. And we have the dead interval of 60 seconds and the hello interval of 15 seconds. Alright, so we don't have any DR yet or any BDR. Sometime really soon, the router is going to elect itself. Not yet. It's going to elect itself as the DR. It's not happening. So this is the hello packet that is going to all the other routers. So if we stand here and we look at the sniffer, we can see these packets coming from 10.0.0.1. So what I'm going to do is go under the router 2, and I'm going to enable that interface with the default configuration, which is 10 seconds of hello time, hello interval, and 40 seconds of dead interval. By the way, before doing that, I can do the debug IP OSPF event. This command will show us the things that are happening in the background in regard to OSPF, all the events that are happening with OSPF. We're going to see that in this screen here. So when I enable that, it says OSPF event debugging is on. So now I can go under the interface gig 0/0 and give it an IP. This is 10.0.0.2 with a /24 subnet mask. And I do a no shot. The interface is up, and I'll do IP OSPF 1 area 0. So see what happens. Here we have the different events that are happening with OSPF. You can see from the theory, we know that this router will never become a neighbor with this router, an OSPF neighbor, because they have different configurations. Here the hello time is 10. There is 15, so it's different. And this is what we see here. We have the different debug messages. I can do you all or undebug all to stop those debug messages. You can see that the interface gigabit 00 is up for OSPF, and after a few seconds we receive a hello packet from 10.0.0.1 in area 0 from the interface gigabit 00, which has this IP here. And we have a problem because we have a mismatch of hello parameters from that router. And what do we have? The dead interval we receive is 60 seconds. However, what we have configured is 40 seconds. The hello interval we receive is 15 seconds, but we have configured for 10 seconds. The mask is the same, so we have no problem there, but we cannot become neighbors because we have this mismatch here. That's why it's still doing the same thing every time we receive the packet. I can go ahead and enable the debug again. Events. Okay, so what I'm going to do now is go inside the router 3, and I'm going to enable OSPF in that router with the proper configuration, like the default configuration. Let's go under the interface gig 0/0 and give it an IP of 10.0.0.3/24, and we'll do a no shot, and then we'll activate OSPF on this interface. IP OSPF 1 area 0. Once I do that, let's see here. Let's go back to router 2. I'm going to show you a lot of packets here, a lot of things that we're going to have. Let me shut down the interface on router 1 so that it won't disturb us. So we won't have anything coming from there. If we go back in router 2, let's see what we have. Here we still have the mismatch from router 1. Oh, okay, let me undebug this. I'll do you all. Okay, so we have the mismatch here, and this is the very first time we receive a hello packet from 10.0.0.3, which is the router 3. It sent us a hello packet here, and then we receive another hello packet. But in this first hello packet, we might have not seen us inside of it, so the state here will still be init, because we receive the hello packet, but we don't see our ID inside this hello packet. And the next time we receive another packet with our ID in it, then we move our communication to two-way, because we see each other now. And if I can go back to the sniffers, let's take a look here. For example, this is what's coming from our router, from the router 3. Let's see if there is any. So here we don't have a neighbor inside yet, and let's go down until here. Okay, if we look at this packet here, it's a hello packet. Yeah, type 1 hello packet. We can see that under neighbor we have the ID of the router 2. So when router 2 receives this, it knows that we know it exists, and it will consider either moving on with the adjacency to become fully adjacent, or we can also stop at this level and stay in a two-way state if one of us is not a DR or a BDR. We're going to see that next. So that's what's happening there. Let's go back to the debug. And then after that, we send DBD to 10.0.0.3, which means that we are sending a database description packet to the neighbor. This is router 2. Yeah, we send the packet to the neighbor, so we know it's there, and we are now electing the DR or the BDR. We did the election. The BDR is .3, the DR is .2. I'm going to show you what is happening here. What are the conditions to become the DR or the BDR in the next lesson? And then we have the MBR negotiation. We are the slave. So this is the X_start state already. You can see here. State X_start, because this is where you negotiate which one is a slave and which one is the master, and the master is going to poll for information or to poll information from the slave. And after that, we go to the exchange state, where we receive and send DBD and so on, and all the other details. And at a certain point, we're going to start the loading part. We see here exchange done with 10.0.0.3. We know what we need, and then we send the link state request to the other router to tell us exactly what is inside, or to tell us exactly the information that we are missing or that is outdated on our end. So we have the link state request sent, and then we send the BDB and so on. So it's an exchange of a lot of packets going on between the router 2 and the router 3 just to become neighbors. At a certain point, you can see synchronized with 10.0.0.3 the state is now full. So we went from the loading state where we exchanged the information. Right now we don't have too much to exchange because we only have one interface on each router, so it's going to be very quick. So we go from exchange to full, and then we are fully adjacent. And if I go in this router and do show IP OSPF neighbor, we have one neighbor inside our database, and we are in a state of full, and it's a BDR to us. So that's what we can say about the neighbor adjacency, and you can spend some time playing with this, changing all the parameters and see what's happening inside the topology. It will actually help you understand most of what we saw in this lesson. And I also have a link leading you to a Cisco document where you can read more details on what we just mentioned here. And if you're watching this on YouTube, as I said, this is on kbtrainings.com/CCNA. This is where you can get the whole course, and you will study to get your CCNA 200 301 to start or boost your career. And if you like what I'm doing here, consider subscribing and you will not miss one of my next videos. Also like this specific video and share it with your friends if you find it useful. Thank you so much for watching, and I'll see you in the next video here on KBTrainings. Bye.